right, I'm really happy to introduce Matt and Marc from Bastille. And we're going to kick off the real meat of the technical conference here. You might have noticed there's been no math or code yet. We're going to get things rolling with a cybersecurity talk. So with that, it's up to you guys. And if everyone could be quiet, if you guys want to continue conversation, please head out the doors. Thank you. All right, let's go.
Hi. So is my mic on? You guys hear me?
There's a switch on the side.
That would help. Better? Cool. So hi, everyone. My name is Matt Knight. This is Marc Newlin. We're going to be talking about some applications of software-defined radio in security research. And in particular, we're going to focus on some offensive wireless techniques, particularly ones that target the physical and MAC layers of different communication systems. And this is all related to some work that we did earlier this summer in putting together a wireless threat taxonomy. Essentially what we did was we looked at some of the most high-profile, or most interesting high-profile attacks that have happened in the past couple of years. And we kind of pulled out what was common among them and put them together in a format that we presented at DEF CON. So what we're going to show you is an abridged version of this talk that we presented at DEF CON. If you want to see the full version, the video will be out soon. But we're excited to be here and share this with you today. So again, we're security researchers with Bastille Networks. We have both been in the wireless space for the last couple of years, but really our passion is security. We're excited to be here. So we're going to begin with a quick run-through of just some background of the tools and techniques that have been used to look at networks over the last 20 years or so, the evolution there. And then we're going to get into the abridged version of our wireless threat taxonomy. And for each type of attack, we're going to highlight kind of the mechanics of how the attack is performed and the impacts that it enables. Then we're going to tie it back to analogs that exist on wired networks. And this is the part that we were most excited about with bringing this type of content to DEF CON. Because at DEF CON, you have people with very diverse background in computer science, information security, electrical engineering, et cetera. But there's not always a concentration of wireless experience. So what we hope to do with this content is take wireless security and kind of distill it down into parallels that can be understood from people by people with different backgrounds. And to round this all out, we have examples and demos of these attacks that we're going to be highlighting. And finally, we'll leave you with some suggestions on how to apply this information. So a quick run through of some of the evolution of the devices and techniques here, or technology and techniques that are used to secure networks. Packet sniffing back in the 90s was largely a reduced experiment versus what we have now. There were really two protocols one had to concern oneself with. You had 802.3, which is Ethernet, and 802.5, which is token ring. And if you wanted to look into those, it likely involved buying an expensive proprietary computer and running expensive proprietary software on it. So that's not great. Fast forward to 1998, and Ethereal comes out. Ethereal is since rebranded. We now know it as Wireshark. And essentially, that took that expensive proprietary solution and turned it into something open source and commodity that could be used by just about anyone and extended to suit whatever purposes a user might have. Now, if we look at what goes into packet sniffing since the 2000s, it's a little more complicated. The set of protocols we have to look at has expanded quite a bit. And one thing that you may notice is that tons of these are wireless. So in the early days, if you wanted to start looking at some of these proprietary protocols, you had to get into the software-defined radio market with one of these early SDRs, which in the 2000s was expensive proprietary solution, mostly restricted their use to primarily academic and government functions. Again, proprietary, expensive, not that interesting. Fast forward to 2012, and we all know what happened with the RTL SDR. And you combine that with the acceleration and adoption of GNU Radio by the open source and information security community, and this is starting to get interesting. Now it's 2017. There are software-defined radios at every price point, varying different levels of capability. This technology is fully commodity, and the industry and the open source community have really risen and responded to that. So the wireless space in 2017 is interesting because 802.11 is really just a piece of the puzzle. With the growth of the Internet of Things and mobile technologies, we have enormous diversification in wireless stacks. There are physical layers targeting just about every application, every use case, and many of these are being used to connect embedded systems. which is an area that we really like to focus on because embedded security, we all know, is a disaster. And there are good reasons for it. It's because embedded systems are really designed to accommodate compromises. And that's because oftentimes you have to develop systems that they have to be cheap, so they can be built out in volume. Oftentimes they have to run on battery, which will limit the type of computation, the amount of computation you can do on it. Oftentimes they're connected over networks with limited bandwidth, so it can be hard to push firmware to them. Additionally, some of them, by virtue of the type of memory they use, if they're using one-time programmable memory, they might not even be able to receive software updates at all. So when you look at this, it's not a great situation. And there's a picture that I'd like to draw your attention to on the left-hand side of the slide, which I think kind of ties this all together, why embedded security is such an interesting challenge. In that picture are 3 literal embedded systems. They're roadway sensors that are literally buried in concrete. So you can imagine that getting software to those is quite a bit more complicated than Patch Tuesday if you're a sysadmin. So when you pair this with a industry reliance, historical reliance on security through obscurity, it means that for us as security researchers, we've got loads of targets to go after. So with that whirlwind run through, that brings us to our RF attack methods, our methods of wireless exploitation. And this is our wireless threat taxonomy that we introduced at DEF CON. We've reduced it quite a bit for this shorter format, but we'll take you through 2 techniques that we think are interesting. So for each technique, we're going to walk through the method for how the attack is performed, the impact that it enables, that is, what you can do to the victim, an equivalent analog, if one exists, on a wired or IP network. And again, that's just trying to take this content and make it easy for people who don't have wireless background to understand. I acknowledge I'm preaching to the choir, but this is the perspective that Marc and I are approaching this from, because we think that this content is relevant to information security practitioners kind of all backgrounds. We're going to discuss the limitations on these attacks, whether they're intentional or incidental. An intentional mitigation would be a defensive mechanism that a developer could build into the product. An incidental limitation could be physical layer limitations or things just by virtue of the RF medium that make it challenging. And finally, we'll tie it up with some examples and demos. So these are the 7 categories that we presented at DEF CON. We essentially boiled the different types of RF attacks that we've seen in the last few years down into these categories. Unfortunately, we don't have time to cover them all, so we're going to focus on jamming and some physical layer manipulations that enable us to do selective receiver targeting. So with that, I'm going to kick it off to hand it over to Marc, and he's going to kick off the conversation with jamming.
So the premise behind jamming is pretty straightforward. So imagine we have Alice and Bob. They're in a quiet room trying to have a conversation. They can communicate just fine. And then Donald shows up and blasts a bunch of nonsense. And Donald's nonsense is so loud that Alice and Bob can no longer talk. And this same thing applies in the RF medium and not just the audio medium. And by jamming devices, preventing them from communicating, we can block traffic on a network or perhaps disrupt the state of the network. And the closest wired analog would be a denial of service attack. But a DOS attack is typically looking at layer 2 or higher traffic. And with a jamming attack, speaking in the RF medium, we're looking at the physical layer primarily. So it's somewhat like a DOS attack, but a little bit lower on the stack. So the big problem with jamming is that if you're trying to jam a system or jam devices from communicating, you cannot listen to those devices at the same time because you're also jamming yourself. And there are also devices that can implement jamming detection mechanisms, which will detect the jamming attack and then change their behavior based on that. And there's some ways around that, as we'll see. So last year, or rather a couple years ago, our colleague Logan Lamb did some research into wireless home security systems. And what Logan discovered is that he was able to jam the wireless link between the wireless door and window sensors in the control panel. And the way this normally operates, you install these in your home, you open a door, you open a window, and then this wireless sensor transmits a message to the control panel to indicate that you have opened the door or opened the window. What Logan discovered is that you can actually jam that link, prevent that message from getting through, and then walk into somebody's home. So he went on Good Morning America with the usurp and GNU radio and broke into somebody's house with their permission. And so for demo here, what we'll do is show in a Faraday cage that we're able to jam this wireless link, open and close these sensors, not have the alarm triggered. Then we'll turn off the jamming, do this again, and we'll see the alarm is triggered. Can you show me how to get up the video? And this is in a Faraday cage because jamming is typically not allowed anywhere you are. So we're opening and closing the sensors, the alarm is not set off, then we'll, in a second, I'll tab over to Can You Radio here, then we'll stop our transmitter, which is just transmitting noise at 345 megahertz, open and close the sensor again, and then the alarm is triggered.
It's an awesome 2-block flow graph.
Yep, I like 0.001 picobalance. And so the problem with this technique is that a lot of devices will implement a jam detection mechanism. And there are some type of smart jamming we can use to evade this. So when you have two wireless devices communicating, as you know, it's not good if they're both transmitting at the same time, because then they will potentially jam each other. So you have something called a clear channel assessment, where a device will pull the power on the current channel it's expecting to use, and if somebody else is transmitting, it will wait until that user is done before trying to transmit. So this data that comes from the CCA mechanism can also be used to detect jamming. So say we have a hypothetical protocol with a packet length of 9 milliseconds. The expected behavior will be the channel being occupied for 9 milliseconds and then go silent. So if the channel is occupied for 10 milliseconds, that indicates non-standard behavior and potential jamming. So what you can do is what's called pulse jamming, or duty cycle jamming, where you turn your jammer on and off to defeat this mechanism. So in this case, we would jam for 9 milliseconds, turn the jammer off, jam for another 9 milliseconds, and turn it off. And this way, we're able to effectively jam the channel while not being detected by this jam detection mechanism. And we're not aware of much public work with duty cycle jamming. Matt's done some work with 802.15.4. Logan did some private work with his home security stuff, but nothing too public. Then there's something called reflexive jamming, which is a bit smarter. And this allows us to target specific packets or users on a network. And the way this works, we receive the packet header, and as soon as we receive the packet header, we make a determination, either the transmitter address or the receiver address or some other feature of this packet. Then as soon as we make that determination, then we can start jamming. And if we can start jamming fast enough, you can actually corrupt the end of the packet and cause a CRC failure and allow us to jam specific packets while still receiving traffic from the network that we actually care about. And this image on the left here, this is called the Roll Jam. This is a device built by Sam and Camcar. There's also some reflexive jamming support built into the Killer Bee framework that works with the API mode and other 802.15.4 devices. And now Matt will take you through some 5-layer selective targeting attacks.
Cool. So this next technique is built on some research that came out of Dartmouth a couple of years ago. And I think that this is a really interesting application of some real kind of fundamental communications techniques back to the security space. And essentially it involves kind of how a protocol grows up and becomes a standard, and then what happens after that. So, or I got that backwards, sorry, how a standard grows up and becomes an applied protocol and some of the implications there. So essentially what this boils down to is the chipsets implement different physical layer standards differently. And the reason why that transpires is because when a protocol or standard is developed, you have your standards body, your IEEE or your 3GPP. They get together in a room over a series, they have meetings and they talk about what they want their PHY to look like, what features they want it to have, and they ultimately boil those conversations down into a nice condensed 4,000-page document that tells you exactly how that standard should work. That document then gets either distributed or purchased by chipset manufacturers, who then have to interpret that, right? So they have to read that document, figure out exactly how all the nitty-gritty techniques work, and then take that and turn that into silicon. And as you might imagine, there are lots of places for that to go awry, but also there are legitimate places where they have to make their best determination of the best way to implement the standard as closely as they can. So there can be lots of gray areas for corner cases to emerge in different physical layer implementations. So we can abuse that. We can essentially characterize and fingerprint the deterministic state machines that these RF physical layers are built on. And with that characterization, we can then send standards non-compliant transmissions that exploit different corner cases in each PHY. So the example that we're going to show today is with targeted receiver evasion. And this could be used to essentially evade a wireless intrusion detection system. Additionally, this enables fingerprinting. You can figure out what type of chipset's in a device remotely by sending messages that are deformed in various ways, seeing what it acknowledges and what it doesn't. So the analog here, on wired networks, a similar attack has been demonstrated on 802.3 with Ethernet, targeting, I think it was Cisco switches. But this is far more practical and extensible in the RF domain just by virtue of how the RF medium works. Because it's promiscuous and you don't have to be physically tapped into the bus. You just have to be present, proximal to whatever devices you're going after. This is far more interesting. So some limitations here is that it relies on the network participants that you're targeting being on different chipsets. And additionally, not every chipset has a diverse, rich set of corner cases to exploit. But I'll show you an example in just a minute of using this technique to evade 802.15.4 receivers. So essentially what I'm going to do is I'm going to use 3 hardware radios in demonstrating this. However, GNU Radio is a perfect platform for taking this research further because you can get much more granular control over your PHY. So what I'm going to do is I'm going to use an API mode that has a CT2420 radio on it to send packets that are various levels of deformed. The CC2420 is an interesting radio just because, despite it being a hardware radio, it exposes a lot of control of the physical layer through its registers. And then I'm going to use 2 different receivers. I'm going to use an API mode with a CC2420 in its stock configuration, but then I'm also going to use an ATMEL radio that implements a different state machine because it's made by a different manufacturer. So I'm going to begin by sending 5 standards-compliant packets with the standards-compliant preamble and startup frame delimiter. So that's 4 octets of zeros and then 1 octet of A7. And then I'm going to deform that header by first inserting an extra symbol into the preamble. And you'll see that that will target 1 receiver. And then I'm going to, after I demonstrated that, I'm going to target the other receiver by taking two symbols out of the preamble. And you'll see what happens. See the video okay? Okay. All right, so first 5 compliant messages. You'll see that both receivers receive them without any hesitation. Now I'm going to add 2 extra symbols to the preamble, and you'll see that the RZ USB stick receives those messages while the API mode is completely deaf. It has no idea that these messages are even being sent over the air. Taking 2 symbols out of the preamble, the inverse happens. The RZ USB stick has no idea that it's happening, whereas the API mode's very happy to receive those messages. So again, this is prototyped using hardware radios just because there was some prior art based on them. But GNU Radio is a perfect platform for taking this and running further with it. And I want to give props to the group from Dartmouth that originally did this research. I just picked it up and made the demo and kind of ran with it. But they were the ones that theorized all this. All right, so just to wrap up, essentially what we've done is we've looked at a number of different types of attack techniques, and we've boiled them down into some analogs on wire domains, and also just tried to take this material and generalize it. And ultimately, kind of the conclusion that you can take from this is that certain types of RF techniques, or RF attack techniques, particularly ones that target anonymity and promiscuity, are really hard to avoid just by virtue of how the RF medium works. Because it's promiscuous, because it radiates and you don't have to be physically on a bus, it's a fundamentally different type of network to go after. And it exposes a number of really interesting security considerations for developers to be mindful of. So this is obviously a non-exhaustive list. I'm sure people in this room have gone after RF networks in their own creative ways, but this is really built on some of the high-profile cases that we've really seen in the last couple of years. So some words to leave you with. As attackers, as you begin to transition into offensively looking at these systems, always go after low-hanging fruit first, because especially with these embedded systems, there are oftentimes very easy ways to knock them over, such as things just being unencrypted, unauthenticated, no sequence numbers, so you can do replay attacks, things like that. Oftentimes they use primitive cryptography, where you can grab a key out of the air and then plug that back into your transmitter and keep running with that. But after this, complexity goes up in a hurry, where you have to start tracking state and perhaps denying legitimate participants. So really start with the easy stuff and go from there. Additionally, if you have experience attacking wired networks, you'll find that there are analogs all over the place in the wireless space. Additionally, leverage open source intelligence. So those are things like FCC data sheets, or FCC regulatory filings and data sheets, because that will make this process a lot easier. And if you want to learn more about some techniques of how to actually apply that information, Marc actually gave an entire talk on this at Hack in the Box in Amsterdam in 2016. It's a great condensed source of information on how to apply this information. And then as communications system developers, I'm preaching to the choir here, we all know this, but this is the golden age of RF hacking. And that's because software-defined radio has been commodity for over 5 years, and because the open source community is so strong. There's been a lot of momentum behind this space and an increasing adoption of these techniques by the security community. So every wireless PHY is in scope now. There's really no safe harbors when it comes to embedded communication systems. So if you're an attacker, or you're interested in playing offense, go out and get it. It's very easy. If you're a defender, be aware that the open source community is they kind of have the scent and are on the trail here, are on the hunt here, because so many of these systems are so vulnerable. So if you want to learn more about some kind of offensive applications of software-defined radio, we've published quite a bit over the last 2 years. We have a series that's all about physical layer state machines, how to reverse them, and how to find ways to exploit them. We're actually giving another installment of this with some new techniques and devices at 44Con later this week. I think there will be a video out from that. Again, I mentioned Marc's open source intelligence research. I did some work on reverse engineering the LoRa protocol that I talked about here last year. So I encourage you to check this out if this is interesting. I want to acknowledge my team at Bastille for being a great place to work. And I also want to acknowledge everybody in this room for all the work that you've done. Marc and I wouldn't be here if it wasn't for the foundation that GNU Radio laid. The fact that it makes it so easy to get into the space and apply these tools to different domains. So thanks very much. We're happy to take questions with whatever time is left.
All right. And actually, Josh, if you want to come start setting up. Huh? You're being bugged? Oh. Perfect. Okay, got it. So my first question, did you say that GNU Radio was on Good Morning America?
Yeah, our colleague Logan Lamb used GNU Radio and a USRP and went and broke into somebody's house on Good Morning America a few years ago.
Why doesn't anybody tell me these things?
There's an awesome video. He's sitting in the back of literally a white panel van with a usurp and a laptop.
Oh my God. All right, that might not be the best imagery. Okay, anyways, so questions for Matt and Marc? No? Oh, we got one. Let me get you, Mike, so your question gets recorded.
Oh, boy. Now I'm doomed for all eternity. So dumb question. Whenever you guys are doing your breakout of attacks and techniques, do you ever look into trying to actually exploit any free space fields inside a lot of the protocols, or are you mainly trying to play nice and use the protocols legitly?
What do you mean by free space?
So whenever we've done research with AIS and a couple other stuff, you have a lot of fields where the actual R parameter space says that you have 16 bits, but you only see them use 8. Do you ever try any kind of fuzzing or anything like that on your attack chains?
Yes, I think Marc can speak to that. He's done a lot of fuzzing.
Yeah, so I've with my wireless mouse and keyboard research, I did a lot of fuzzing into exactly that. There were a lot of cases where there were undefined fields that had unexpected uses.
Have you noticed a lot of hits with that, or has it been kind of one-off thing?
Only in the space of the mouse and keyboard stuff is where I've done the work with that, but most of the protocols had a lot of strange behaviors that weren't documented and weren't expected just by modifying some of these fields in the packets.
All right, if that's it, thank you very much, Matt and Marc.
Thank you.
Let's get you set up. Nice job, guys. And I think one of you needs to hand your lavalier to Josh.